Okay, this is the review for test number 1. Question 1, this comes from section 2.1 of the 7th edition book. This is a piecewise function. You're supposed to evaluate the function f, which is this function here, when x equals 8, when x equals -1, and when x equals 6. Now, biggest thing students forget with a piecewise function is that this is a function. You've got to remember the definition of a function. For every one input, there is one output. So I can't plug in 8 into this piece and to this piece of the piecewise function, because that would produce two different outputs. So you've got to figure out where exactly this 8 goes, and that's why you have to look at these parts of the piecewise function. If your x value is less than or equal to 6, you plug it into the top piece. If your x value is greater than 6, you plug it into the bottom piece. Now our first input is 8. 8 is definitely greater than 6. So this 8 is going to go into the bottom piece. 2 times 8 is 16. So f of 8 equals 16. For the next one, f of -1 would fit into this piece. X is less than or equal to 6. So you take a -1 and place it in to this bottom piece here, or sorry, rather the top piece. -1 squared is 1. 6 times -1 is -6. 1 plus -6 is -5. And finally, f of 6. Now you got to look real carefully here. It still fits into the top piece, because if x is less than or equal to, and that's the key, it's equal to 6, you still use the top piece. So 6 squared plus 6 times 6, that's 36 plus 36, which is 72. And this second question is also from section 2.1. This is what was called the difference quotient in your textbook. And the way I outlined it during the lecture was to think about this problem being broken down into 3 pieces really. First, find f of a, then find f of a plus h. Once you found those two, then you can go about putting it all together with this difference quotient. So first of all, f of a, if you plug a into the f function in place of that x, you'd have 4 times a squared plus 1, which is just 4a squared plus 1. Be a little more careful here. F of a plus h, that has to replace the x into the f function. So I'm going to put 4 parentheses squared plus 1, because that's what the f function is. It's 4 times an input squared plus 1. The input becomes blank, and you're going to replace that blank spot with a plus h. One of the tendencies for students is to want to distribute the exponent here. That can't happen. A plus h squared is a plus h times another a plus h. So if you distribute these two parentheses together, you can have an a squared, and then you're going to have an a times h here and an a times h there, so you're going to have 2 a times h terms, and then plus an h squared term. And then distribute the 4. And there aren't any like terms there to combine. So that's 4, or that's f of a plus h, and here we had f of a. So this is f of a, this is f of a plus h. So now we can put that together over here for the difference quotient. So first f of a plus h we subtract f of a, now I'm going to put f of a in parentheses. That way I'll be subtracting the entire function f of a. That's all divided by h. Now here you'd have to distribute the minus sign. So this is really minus 4a squared minus 1. So if you look carefully now, we're going to have a minus 4a squared. It cancels with that positive 4a squared. And then, remember this is really a minus 1 because we distributed that minus sign. So that minus 1 is going to cancel with that plus 1. So what we have now is 8h plus 4h squared all over h. And if you look in the numerator, both terms in the numerator have an h as a common factor, so if you factor out an h, okay, and then this h that you factored out can cancel with that h in the denominator. So this would be evaluating the difference quotient. Question 3, question 4, and I believe the next question, question 5, these are all also from 2.1. Question 3 is to find the domain. So the biggest issue with this type of a function, this is called a rational function, is you can't have the denominator equal to 0. You can't divide by 0, it's undefined. So what you really want to figure out is when is this equal to 0? 2x plus 6 cannot equal 0. So this is a simple equation to solve. Subtract 6, divide by 2, and it says here x cannot equal negative 3. I prefer that you write it in interval notation. So negative infinity, instead of going all the way to positive infinity, we have to take a break here at negative 3. So what this means, this interval right here, is all real numbers except negative 3 is excluded. This would be the domain of f. You know, it's a similar function here. We have a rational function. And it's again true that the denominator here, x squared minus 4, cannot equal 0. Okay. So if you have the 4 to the other side, and then square root both sides, x cannot equal plus or minus 2. So again, just following with what the book prefers. The book prefers, our textbook prefers interval notation. So we've got every real number except for negative 2 and positive 2. So we're going to have a couple of intervals from negative infinity to negative 2, and then from negative 2 to positive 2, and then from 2 to infinity. Now, let's see, before we get to number 5, it might be wise, I'm just going to add one, like question 4, part B. Completely new problem though. F of x is equal to the square root of 3x minus 6. This is another type of function that was in your homework from section 2.1. You'd have to find the domain of a function like this. Now with a square root function, you can square root 0. You just can't square root anything that's less than 0. So in order for the square root of 3x minus 6 to be defined, 3x minus 6 must be greater than or equal to 0. If it weren't greater than or equal to 0, we couldn't take the square root of it. So this is a inequality, a simple inequality to solve. Add the 6 to the other side. Divide by 3. So this is saying that any value of x has to be greater than or equal to 2 in order for this function to be defined. So as an interval, since it includes 2, I'm going to use a bracket, and any number larger than 2 would be from 2 to infinity. Okay, question 5 here is also from section 2.1. This is another domain. Find the domain. This one's a little trickier. There are two things to consider. This is a rational function, so the denominator here cannot equal 0. We also have a square root. Now, in order to square root x, it must be true that x has to be greater than or equal to 0. So, got to figure out how both of these fit together. Now, the top part is pretty much done. X has to be greater than or equal to 0 in order for this to work, the numerator. But what about the denominator? X squared minus 16x plus 55. We're going to have to factor that. So two numbers that multiply to positive 55 that add to negative 16. That's going to be negative 11 and negative 5. So it's x minus 11 multiplied by x minus 5. So x cannot equal positive 11, and x cannot equal positive 5. So there are really three things to consider. X has to be greater than or equal to 0, but it can equal 11, and it can equal 5. So to put this all together, starting at 0, we can't go all the way to infinity like this, because that would include 11 and 5. So we have to make a couple of intervals from 0 first to 5, from 5 to 11, and from 11 to infinity. Again, questions 6 and 7 both come from section 2.2. These were towards the end of your homework. Determine whether the equation defines y as a function of x. So, two ways I guess you could think about this. Graphically, if we were to produce a graph of either one of these, it would have to pass the vertical line test. Or, if you plugged one number in for x, you'd have to get a single number out for y. One number in, one number out. That's the definition of a function. Here's an example of what I mean. If we wanted to make an xy chart, I plugged in a number for x, 2 for example, plugged it in right here. 2 squared is 4. Then subtract 4, and then divide by 3. We place one number in for x, we got one number out for y. So, I mean, that worked for x equals 2, but there may be some x value for which that doesn't work. Here's another way you could think about testing this. If you solved this equation for y without plugging any specific values in for x, you could subtract the x squared, the other side, and then divide everything by 3. And what you're left with is y equals negative x squared divided by 3 plus 1. This is a quadratic equation, or a quadratic. This would be the graph of a quadratic, which is a parabola. It looks something like this. It's facing upside down because of the minus sign in front of x squared. The point is, this passes the vertical line test everywhere. So, determine whether the equation defines y as a function of x. The answer is yes, this one does. Okay, question 7 is a little bit trickier. So, here's one way you could think about question 7. So, if shows another number here for x2, and then plugged it in. We have 5 times 2 minus absolute value of y is equal to 0. If I added the absolute value of y to the right side, I'd have 10 is equal to the absolute value of y. Now here's where you really got to think. The absolute value of a number y is equal to 10. What that means is y could be 10 or y could be negative 10. If the absolute value of y is equal to 10, that means y could be positive 10 or y could be negative 10. So we had one input, but it gave us two different outputs. So this would not be a function of x. Now question 8 is from section 2.3. Getting information from the graph of a function. In 2.3 we talked about evaluating a function graphically, finding domain and range on a graph, finding the intervals of increasing and decreasing. So evaluating a function graphically, I think it's quicker than evaluating a function algebraically. Normally, if you were to evaluate g of negative 5, you would place negative 5 into the equation of the function and try to find it that way. But graphically it's much easier. This is an x value right here. Negative 5 is an x value. So you find a value of negative 5 on the x-axis, and the value of g is the point on the graph at x equals negative 5. The y value there, or the vertical height, is 3. So g of negative 5 is equal to 3. Now, to be a little more careful on this one, part B, g of 1, remember this still is a function, so it wouldn't be possible to say, alright, g of 1 equals this, or it equals that. It can't equal two different things. One input gives you one output. So you have to look real carefully right here. This is where x equals 1. Okay? And at first glance, it would appear that, well, maybe there's two different answers, 1 and 3. But if you look closely, that's an open circle. That means the function isn't defined up here. When x equals 1, the only part of the function that's defined is that filled in circle. So g of 1 is equal to 1. In other words, this is saying that the point 1, 1 is on the graph. When x equals 1, y equals 1. So finding the domain of the function g. So if we're looking along the x-axis, starting furthest to the left, negative 6, negative 7, negative 8, any of these negative numbers aren't producing points on the graph, so they are not in the domain. Starting at negative 5 produces an output. Negative 4, negative 3, negative 2, negative 1, 0, 1 produces an output, because the point 1, 1 is on the graph. 2 produces an output. 3 produces an output. Anything to the right side of 3 is not in the domain, so the domain is from negative 5 to positive 3. The range, if we're looking at the y-axis here, the smallest number on the y-axis, or the lowest number on the y-axis that has points on the graph, or values of y, is right here at negative 2. Okay. And you've got to check all of the numbers starting at negative 2 and increasing. All of these values are producing points on the graph. Even here, I know there's a little gap right here, but a y value of 2, we have a point right there with a y value of 2. So 2 is in the range. 3 is in the range, including 3, because there's a closed point right there. So the range would be from negative 2 to positive 3. Now finding the intervals for which g is increasing, the thing you've got to remember is only x values. When you're stating intervals of increase or decrease, you're only using x values. So reading the graph from left to right, the first thing this does from left, this graph does from left to right, is it decreases. The graph is decreasing, or the y values are decreasing right to there. But starting at this x value, the graph begins to increase again up until this x value, and then the graph decreases again. So the intervals for which g is increasing, the only part of the graph that's increasing is this piece of the graph right here, and it's between this x value and that x value, so it's increasing from -1 to +1. And the other portions of the graph, this portion of the graph right here and this portion of the graph right here, between -5 and -1, and between +1 and +3, those are portions of the graph for which g is decreasing. So it's decreasing from -5 to -1, and from 1 to 3. Okay, question 9 is from section 2.4. The title of that lesson was the average rate of change. So really what it boiled down to was the slope formula f of b minus f of a all over b minus a, where those would be your a and your b values. So this is really nothing more than evaluating a function. We'd have f of -2 minus f of -3 all over -2 minus -3. So f of -2, I'm going to do these separate, and then f of -3. Let's start with f of -2. If I plug a -2 into the f function for the t's, it's going to be -2 squared minus 9 times -2. -2 squared is 4. -9 times -2 is 18, so that equals 22. Now for -3, we have -3 squared minus 9 is -3, so -3 squared is 9 plus 27, that equals 36. So f of 2 was 22, and f of -2 rather was 22, and f of -3 was 36. -2 minus -3 is 1. 22 subtract 36 is -14. So the average rate of change between -3 and -2 is -14. Okay, this is an application problem from section 2.4. This graph is showing the depth of the water in a reservoir over a 1 year period of time as a function of number of days since the beginning of the year. So this would be January 1, this would be December 31st. So the water is increasing, or the depth of the water is increasing, and then the depth decreases and then starts to increase again. What's the average rate of change between x equals 0 and x equals 100? Well, since it's an average rate of change, it's still the same formula, f of b minus f of a all over b minus a, and here we have a and b, and we can call this the function f here. So f of b would be the value of the function f when x equals 100. So if we check where x equals 100, you have a vertical distance of 75. So f of 100 equals 75. Now, here, f of 0, go to an x value of 0, check the vertical distance there, and it's 50. So we have f of b, which was 75, minus f of a, which is 50, all over b minus a. 75 subtract 50 is 25. 100 subtract 0 is 100. 25 divided by 100 is 1/4. Now that's using the formula. The way initially the way average rate of change was introduced in the lesson in section 2.4 graphically was all the average rate of change is between 2 points is the slope of a line that connects those 2 points. So if you were to draw a straight line between these 2 points when x equals 0 and x equals 100 and count the rise over run, the rise is 25, the run is 100, so the slope would be 25 divided by 100, which is exactly what we found over here. Now, question 11, question 12, maybe a few others here. These are all from the next chapter, chapter 3, section 3.1. Okay. Express the quadratic function in standard form. Remember, another word for standard form, some textbooks call it vertex form. And find either its maximum or its minimum. Now we can decide that right now. This is a parabola, f of x equals x squared plus 4x minus 3. And since the leading coefficient is positive, it's positive 1, that means the parabola is facing up, which means its vertex is at the bottom. So it would be, we know it's going to have a minimum value of some sort. So the implied directions here to express this quadratic function in standard form is to use the complete the square method. So the way I showed it in class was to move this constant to the same side as the function f. I have f of x plus 3 is x squared plus 4x. And where that negative 3 used to be, we're going to add a value to complete the square. So the function, or the formula rather, is half of the b value raised to the second power, where this is b right here. So half of 4 is 2, 2 squared is 4. So adding a value of 4 to the right side completes the square on the right side, but since this is an equation, whatever change you've made to the right side, you've got to make the same change to the left side. Okay. And the reason for adding a specific value of 4 is because now this expression here factors into x plus 2 multiplied by another x plus 2, which can be written as x plus 2 squared. Subtract the 7 back over, and that would be the same function but written in standard or vertex form. One reason for writing it in vertex or standard form is vertex is immediately identified as part of the expression. X plus 2 means the graph moves 2 units to the left. Minus 7 means the graph moves down 7 units, which places the vertex at negative 2, negative 7, and that would be the minimum value. Negative 2, negative 7. What you really ought to expect on the exam, there were much more challenging problems than this in your homework. So I don't want you to just look at this one problem and think, alright, we got it easy. Some of the ones in your homework had a number in front of x squared other than 1. For example, if you wanted to think about a part B here, something like this. X squared plus 18x minus 4. It's the same process, you just have to be a little bit more careful. So if you start by moving the negative 4 to the other side, adding it to the other side, so f of x plus 4. Now here's where it gets different. This negative, or this 3 rather, needs to be factored out, those two terms. And I'm going to close a parenthesis in such a way to allow for a number or a value to be added to this expression. So again, it's the same little formula here, half of the b value, not the original b value, but this b value right here, which is 6, half of that is 3, 3 squared is 9, but this is still an equation. Whatever changes I make to the right side, you've got to do the same thing to the left side. You've got to be careful. I really didn't add a 9, because if I took this 3 and multiplied it back into the parenthesis, that 9 would become a 27. So I really added 27 to the right side, so you've got to add 27 to the left side. That makes it 31. So we've got f of x plus 31 equals 3. And then this expression right here, x squared plus 6x plus 9, factors into x plus 3 squared. Now you can move the 31 back over by subtracting. So a little bit more to keep track of in that sort of a problem. Okay. Question 12. This would have been in one of the application problems from the homework in section 3.1. Ball is thrown with an upward velocity of 80 feet per second. Its height after t seconds is given by this formula. What's the maximum height attained by the ball? So if you look carefully here, let me rewrite this so maybe it's easier to see. This is the equation of a parabola, and since it's negative 16t squared, the parabola, if it were graphed, would be facing upside down, and so the vertex would be a maximum. So without really stating it, what this question is asking is to really find the vertex. So it can be done the same way as this previous question, but there's perhaps an easier way or a quicker way. This was also introduced in lesson 3.1. There's a vertex formula. The opposite of b divided by 2a, but you got to remember this is equal to the x value of the vertex. In this case we don't have x values, we have t values, so this vertex formula is going to give you the t value of the vertex, where t is in seconds. So the opposite of b is going to be negative 80, and then 2 times a okay, and then this would need to be done on a calculator. Probably want to use decimals, unless you want to keep it as fractions. It's up to you. You are allowed to use a scientific calculator. I'm going to be using this graphing calculator just because that's the one I have available, but you're going to want to use your scientific calculator. 80 divided by 32 is 2.5. And that's 2.5 seconds, remember, because this is the value of t. So the ball reaches its maximum height after 2.5 seconds, but the question is, what is the maximum height attained by the ball? So you have to take this 2.5 and plug it back into the equation for t. Again, probably be easier to just do this on a calculator. Negative 16 times 2.5 squared plus 80 times 2.5. This ball reaches a maximum height of 100 feet. Okay, this is another Application problem from section 3.1 is pretty much the same as the problem previous. Manufacturer finds that revenue generated by selling a certain number or a certain commodity is given by this function where revenue is measured in dollars. What is the maximum revenue and how many units need to be manufactured to obtain this maximum? Key word here is maximum, and tying that back into this, you can see that this is the equation of a parabola, and since it's a negative leading coefficient, the parabola is facing upside down again, so this parabola has a maximum. And if we were to graph this, the x-axis is the number of units sold, the r-axis is, or the y-axis rather, or the r-axis is revenue. So how many units does it take to reach this maximum revenue? That's what it's asking. Again, I would use the vertex formula, the opposite of b, divided by 2a. So negative 160 divided by 2 gives negative 0.4. So negative 160 divided by 2 times negative 0.4 is 200. So since this is x, you got to remember this is number of units, so you have to sell 200 units to achieve maximum revenue. But what is the maximum revenue? So you got to figure out how much you're going to make if you sell 200 units. So you got to put 200 back into the function. So it's 160 times 200 minus 0.4 times 200 squared. You're going to make $160,000. Looks like. Maximum revenue of this commodity is to sell 200 units, and you make $160,000. Now you think, well, if you want to make more money, just sell more. But what isn't described here in the problem is the more you make, or the more you sell, the more you have to make. And apparently for this product, the cost starts to increase after 200 units. So it wouldn't be as cost effective to produce more or to sell more. So anyway, now getting back into chapter 2 again. This would be from section 2.6. So suppose the graph, describe how the graph of the function can be obtained from the graph of f. So really what they want you to write a statement that describes what's happening here. So f of negative x, that's the change right there, and this would be a reflection. And since it's inside the function, it affects x, so all the x values are being reflected. So the positive x values become negative x values. So if you're thinking about a graph, all the positive x values over here become negative x values over here. So this would be a horizontal reflection. About the y-axis. Okay, question 15. Suppose the graph of f is given. Same thing, same question. Different things are happening here, though. We've got 7 times f of x minus 3. So the 7 is a transformation and the minus 3 is a transformation. Both of these transformations are occurring outside of the function. Anything that occurs outside the function is a vertical change, but it affects the graph differently. Since the minus 3 is adding or subtracting, the 7 is multiplying. They affect it in different ways. The minus 3 is just a shift, so it's a vertical shift. Down 3 units. But then we have a vertical stretch. That's what the 7 does. It's a vertical stretch by a factor of 7. Okay, question 16. We've got 4, we've got a plus 5, and we've got a minus 3. So it's actually a very similar situation with the 4 here and then the negative 3 here, but the difference here is we have an x plus 5. The plus 5 is inside of the function. Anything that occurs inside of the function affects the x value, or the horizontal component of the graph. And because it's adding or subtracting, it's just going to be a straight up shift. It's not going to change the shape, it's just going to move the graph, as does this minus 3. But this is a vertical shift to minus 3. Plus 5 is a horizontal shift. So a vertical shift down 3 units. We've got a horizontal shift this one you just got to remember, it's inside the function's opposite. X plus 5 moves the graph to the left 5 units. And we have another vertical stretch. By a factor of 4. Okay, the way a problem like this was outlined in the discussion for section 2.6 was to identify some of the easily identifiable points on this weirdly shaped graph. So we've got negative 5, 0, got 0, 5, 2, 1, we've got 5, 2. So there's two different things that's happening here. We've got this negative in front of the f of x, and we've got that plus 3. So both of these are occurring outside of the function, which means they're going to affect the y values. It's a vertical change. So if it occurs outside the function, you do exactly really what it describes here. You make all the f of x or y values their opposite and then add 3. So essentially what's happening is the graph moves up 3 units and then gets reflected over the x-axis. So if we were to make a new table of values, nothing happens to the x values. The y values change. You add 3 to them and then make them all negative. Now you got to do things in the right order of operations. You multiply here by the negative before adding the 3. So first thing is to make these all negative. So it would be, if we did like an intermediate column here of just the y's, we'd have 0, negative 5, negative 1, negative 2. That's what the negative sign does. And adding the 3, we have 3, negative 2, 2, and 1. So we have negative 5, comma 3, 0, comma negative 2, 2, comma 2, and 5, comma 1. So you can see that the graph has been reflected vertically. It's been flipped upside down, but then it's also moved up 3 units. Okay, question 18. The original function here, f of x, is just a plain old x squared graph. You've got to figure out what the function or the equation is for the g function here. So a couple things have happened. It's moved to the right 4 units, up 2 units, and it's flipped upside down. So since it's flipped upside down, I'm going to put a minus sign outside of the function. That's important, that it's outside the function. That would be a vertical reflection. And since it moved 4 units to the right, that's going to be an x minus 4. Any horizontal change needs to be inside of the function. Okay? One of the biggest mistakes students make is to write x squared minus 4, and they say, well, it's still inside the parenthesis, and that's true, but the function here isn't just a parenthesis. The function here is something that's being squared. In order for negative or the minus 4 to be inside the function, it needs to be part of what's being squared. So it is x minus 4 to the second power. And then in order for this graph to move up 2 units, you have to put a plus 2 outside the function. And that was from section 2.6. Kind of going out of order. Number 19, this is another one from section 3.1. You have to build or create a function with this vertex, and that passes through that point 4, negative 5. Now, since they've given us the vertex, easiest thing to do would be to begin in vertex or in standard form. So this is the equation of the quadratic in standard form, where the vertex goes in for h and k. So it's going to be x minus 3 squared plus 1. Now what we don't know, matter of fact, just to make this a little quicker, I'm just going to use y instead of f of x. What we don't know is this value of a. When a changes, that makes the parabola either skinnier or narrower depending on the value of a. So we have to have the correct value of a so that this parabola can pass through the point 4, negative 5. Now by giving us this extra point, they've given us an additional x and y value. Those can be plugged into the function. 4 for x and a negative 5 for y. If you plug those values in, that will allow you to solve for a. I'm going to go ahead and do that. I'm going to plug a negative 5 in for y, leave a as a, plug in a 4 for x, and then follow order of operations. 4 minus 3 is 1. 1 squared is 1. 1 times a is a. So we have negative 5 equals a plus 1. This is, if you subtract the 1 to the negative 5, you get a is equal to negative 6. So the equation is y equals negative 6 times x minus 3 squared plus 1. Now, this is from section 2.7 now, combining functions. Usually with a problem like this, g of f of 5, you'd have two different functions, f of x and g of x, and you'd have some kind of equation here, and you'd plug the 5 into the f function, take that result and plug it into the g function. What you are being asked to do here in question 20 is to do all of that graphically, which actually is a little bit easier. If you work your way from the inside out and just start with f of 5, this right here is the f function, and you have to figure out the value of the f function when x equals 5. So if you go out to the x-axis to a value of 5, 1, 2, 3, 4, 5, 1, 2, 3, 4 right here. So when x equals 5, the f function has a value of 4. So you could write this f of 5 is equal to 4. Now since these two are exactly the same, f of 5 is equal to 4, rather than saying g of f of 5, you can take the f of 5 and replace it with 4 So now you're evaluating the g function when x equals 4. So 1, 2, 3, 4. 1, 2, 3. It's about right there. So 3.5 looks like. Now it's kind of a weird number. It is what it looks like happens. You have to look at this graph real closely, what it looks like, and trace it. It looks like as it comes all the way down, it stops right there. So let's try this again. 1, 2, 3, 4. So this is when x equals 4. If we evaluate now the g function, 1, 2, 3. Looks like g of 4 is equal to 3. Okay. This is an application problem from section 2.7. So there's different types of discounts happening here. There's just a 10% or $10 off coupon, or there's a 40% discount. The way that those are applied actually makes a difference on the final sale price. So if you take 40% off first and then take $10 off, compared to taking $10 off first and then 40% of that, it makes a difference. And that's really the point of this question, is to see which one really is a better deal. Is f of g or is g of f the better deal? So reading through this, suppose only the 40% discount applies. F is the function that's going to model the purchase price if you only get 40% discount. So f, that's where some students really just got to slow down and think about what's happening here. X represents the purchase price, or sorry, X represents the regular price of the cell phone. If you're getting 40% off, how much are you actually paying? You're paying 60%. So you're getting 40% off, which means you're paying, if F is what you're paying 60% of the regular price, so it's 0.6x. Now, this one here, suppose, I'm actually going to write this down here, f of x is equal to 0.6x. Now, suppose only you get $10 off, that would be the g function. So if you have the regular price of the cell phone and you get $10 off of that, it's going to be x minus 10. So now, A and B, A is f of g of x. That means the g function goes inside of the f function. So the f function is 0.6 multiplied by x. Now, rather than placing an x there, I'm going to have an empty spot, because that's where the input goes. The input is the actual g function itself. So we're going to simplify this. It'll be 0.6x minus 0.6 times 10, which is 6. So what this says is you pay 60% of the regular purchase price, or regular price, minus $6. Well, not a bad deal. But B is g of f of x. So the g function says you have some input, and then you minus 10 from that. And the input now is the f function, so the f function goes in place of g. The f function is 0.6x. So here we have 0.6x minus 10. So the natural follow-up question, which isn't actually part of this question here, but the natural follow-up is which one's the better deal? Should you, now f of g means that you apply the $10 discount, or the $10 off first, and then you have 60% off. Whereas here you do the 40% off. Whereas this one you do the 40% off first, and then you apply the $10 off coupon. Which one's the better deal? It's taking 40% off and then subtracting 10 from that. So the better deal is g of f. You're going to save a lot more money. Well, a lot more. I don't know. You're going to save more money doing it that way. Okay, question 22 is from section 2.8. Find the inverse. Phrase to remember is switch the place of x and y. So maybe rather than f of x, you could think about that as a y. So switch the place of x and y. Then the second phrase is solve for y. Those are the two phrases to remember. So first thing you do is switch the place of x's and y. So this is going to become x equals y minus 9 over y minus 2. Now this, for this particular problem at least, solving for y can be a little tricky because there's two different y's. So once you've done a few of these, it's pretty much the same process over and over again when you have some kind of a rational function like this involving y. So first thing you're going to want to do is get rid of the fraction by multiplying by y minus 2 to the left and the right side. And then I'm going to distribute the x. I've got xy minus 2x equals y minus 9. What you're going to want to do is get all the y terms, or any term that has a y, get that on one side. Any term that does not have a y, move that to the opposite side. So I'm going to move this y to the left over here. I'm going to take this negative 2x term and move that over here. So we got x, y minus y equals positive 2x now, minus 9. The reason for trying to collect all the terms that have a y on the same side is because now this y, or these y's rather, can be factored out. So I factored out a y on the left side. That left me with a factor of x minus 1. The goal is to get y by itself. That's what solve for y means. And as long as there were multiple y's in the equation, you couldn't really get y by itself. So the importance here is that you factor out a y. Now you have a single y factor that's multiplying this factor of x minus 1. So to move the x minus 1 to the right side, you can divide by x minus 1. We had 2x minus 9 over x minus 1 as the inverse. Okay, question 23. Part of lesson 2.8 was functions that are one-to-one. Now this function here, f, it is a function because it passes the vertical line test. But to test whether a function is one-to-one, you can perform the horizontal line test. So if you drew horizontal lines through the graph, if it crosses it more than once, it fails the horizontal line test. So it is not a one-to-one function. Now the significance of a function not being one-to-one, remember the tie-in here for lesson 2.8 is inverses. If we were to take the inverse of this function as it is, not being one-to-one, the inverse, would be some kind of sideways parabola, and a sideways parabola is not a function. So the significance here is this is a function, but since it's not one-to-one, its inverse would not be a function. So what you're asked to do is find a restricted domain that makes the function one-to-one. So the problem here is it doesn't pass the horizontal line test. If we took, for example, just the right side of this parabola and forgot about the left side of it there, if we just took the right side of the function, that would be one-to-one because it would pass the horizontal line test. So what restriction on the domain could you make that would just allow us to use the right side of the function? Well, the bottom of this function is the point -4, 0. That's where the vertex is, because this moves the graph to the left 4 units. So if we use the same function, x plus 4 squared, but only use the domain of -4 to infinity, that would produce just the right side of the graph. Okay. Now, that's one of the possible answers. We could also choose to use the left side of the graph. Okay, and forget about the right side. So, or you can go from -infinity to -4. So it is more common, though, when you're dealing with a parabola like this, to use the right side. And I'll explain here why that is, because the second part is to find the inverse. So domain, even though it doesn't say, I'm just going to state the range as well. The range is from 0 to infinity. Now, what we have here is y equals x plus 4 squared with this domain and with this range. Now to find the inverse, as we did in the last problem, you switch the place of x and y, and then you solve for y. So square root both sides. Now, here's where the domain and range come into play. This is the domain and range of the original function f of x. When you're finding inverses, you switch the place of x and y. That also switches the domain and range. So the domain now of the inverse is the range of the original function. So the domain now is from 0 to infinity. And the reason that's significant, usually when you take the square root as part of solving a problem or solving an equation, you have to put a plus or minus. We don't need that here because the domain is from 0 to infinity. That means that x is only going to be positive values. And when you take the square root of only positive numbers, the result is only ever going to be positive numbers, not positive or negative. So this domain restriction is very important. That means we don't have to have this plus or minus in front of the square root. And the range, just to make this a complete problem, the range would have been the domain of the original function. Anyway, the last step here is to subtract 4. So we've got square root of x minus 4 would be the inverse. And technically, since we started in function notation, we end in function notation, f inverse of x is the square root of x minus 4. Okay. 24. If you have an x value of 8 that you plug into the f function, that produces a y value of 1. Well, since this is the inverse, you switch the place of x and y. So this is your y value now, so to speak. So it's going to produce the x value, which is 8. So I mean, once you know what the question is asking, how to answer is really easy. It's the same thing here. This is your x value, this is the y value, but in the inverse they switch places, so this would be your y value that would produce an x value of 2. Okay. So this is a true-false statement here that this is the inverse of that, and it says to use the property of inverse functions. This is also from section 2.8. Given two functions f and g, they are inverses of each other if and only if f of g of x is equal to x, and if g of f of x is equal to x. Both of these must be shown to be true in order for these two functions to be inverses of each other. So if we first try f of g of x, it means the g function is going to go inside the f function, so this has to go inside there, so it's going to be 4 minus 8x all over 8. Distribute the minus sign, so the 4's will be gone, and the minus negative becomes a plus, so we've got 8x over 8, which is x. So the first one was true. Now if we test g of f of x, now that means that this function goes, where is it? Let's try that again, right there for x. So we're going to have 4 minus 8 multiplied by 4 minus x all over 8. Now the 8's would cancel, and then if you distribute the minus sign there, you'd have 4 minus 4 plus x. 4's cancel, so you're left with x. So since both compositions f of g of x and g of f of x were equal to x, that proves that f and g are inverses of each other, so the answer is A. It's true. Okay, 26. This is going back to section 2.7, combining functions. You have to add, subtract, multiply, and divide these two functions. So starting with A, 3 over x minus 2 plus x plus 1 over x minus 4. The only way these two expressions can be added together is if they have a common denominator. So this denominator needs an x minus 2. So we have to multiply it on the top and bottom. This one over here needs an x minus 4. So now in the numerator here, on the right side, if you multiply these together, you're going to get see, then we're going to have a minus 2x and a plus x, so minus x minus 2. Over here, we're going to have, oh boy, I'm going to plug in here, we're going to have 3x minus 12. So now we have a common denominator of x minus 4 times x minus 2. We can combine terms in the numerator. X squared minus 2x minus 14. Don't forget to state the domain. You can't divide by 0, so x can't be 4, and x can't be 2. So you could state that as negative infinity to 2, 2 to 4, 4 to infinity. And we'll go back and fix something here. 3x minus x is a plus 2x. My apologies. Okay, really the only difference in part A and part B, I'm going to use the same problem here. That would be a minus sign. So you have to do the same process. You have to get common denominator and combine these two. So you're going to have x minus 4, x minus 2 as your denominator, and now you're combining like terms in the numerator by subtracting. So this minus sign is applied to this entire expression there, so it's minus x squared, and that minus and negative x is really makes it a plus x, so that's plus 4x, and again this minus negative 2 makes it plus 2 when you combine with negative 12, makes it negative 10. And it's the same domain, negative infinity to 2, 2 to 4, 4 to infinity. Now when multiplying, you don't have to have a common denominator, which makes it nice. So you go back to the original functions here. And these can just be multiplied together. Numerator multiplied to numerator, denominator multiplied to denominator. And again, it's the same domain. So this domain right here, just copy it down there. The one that's a little different, at least in terms of the domain, is part D. If you're dividing, these, when you divide fractions, you change the last fraction to its reciprocal and then multiply. So this is really 3 over x minus 2 multiplied by x minus 4 over x minus 1. And again, multiply straight across. So 3x minus 12 over x minus 2 times x minus 1.